In this module, I'm going to introduce Fermat's Little theorem. Although it's called a little theorem, it is quite useful and it plays important role in one of the applications that we're going to study for cryptography. The reason it's called a little theorem is because the proof of it is fairly straightforward, although we are not going to get into the proof here. So this is what the theorem says. Let p be a prime number. Let n be an integer that is not divisible by p. In that case, if I take n to the power p minus 1, this is equivalent to 1 in modulo p arithmetic. Note that what this means is n to the power p minus 1 mod p is 1 mod p, which is same as 1. Another thing we can observe from the same thing is if I multiply by n on both sides, then I will have n to the power p is n mod p. So let's look at an example. Let's say the prime number that we're looking at is 17, n is 21. In that case, 21 to the power 17 minus 1 is this one huge number, but if we do modulo 17 arithmetic, then it would be 1. If I take 21 to the power 17, I have another huge number which is equivalent to 21 mod 17, which is 4. Note that the above result may not hold if p is not a prime. So for example, if I do modulo 4 arithmetic, let's say I do p equal to 4, in that case 7 to the power 3 is not 1 mod p, it is in fact 3 mod p, and this is something you can verify. Same way, 7 to the power 4 is 1 mod p and it's not 7 mod p. There's a special case where we set n is equal to 2. In this case, we can see that 2 to the power 3 minus 1, that's 2 to the power 2 mod 3 is going to be 1. 2 to the power 4 mod 5 is going to be 1. 2 to the power 6 mod 7 is going to be 1. We can take some bigger examples. 89 is a prime, so 2 to the power 88 mod 89 is also going to be 1. This holds true for every prime, but the converse is not true. In other words, it's possible that 2 to the power n minus 1 mod n is equal to 1, but n is not a prime. So for example, if we take p is equal to 341, then 2 to the power 340 mod 341 is 1, but 341 is not a prime. Now, one way we can use this theorem is to compute examples like 5 to the power 2003 mod 7. So the first solution is what we studied earlier. We write the number in binary, and then in this case we have 2003 written in binary like this. Now we are going to compute 2 to the power 0, 5 to the power 2 to the power 0, 5 to the power 2 to the power 1, 5 to the power 2 to the power 5, and so on. So first we can compute 5 to the power 1, which is 5, 5 to the power 2, which is because this bit is 1. Then the next one we have to compute is 5 to the power 16, because this bit is 1. Then we have to compute 5 to the power 64, because this bit is 1, and so on. Now remember, the way we can compute this is we can take 5 to the power 2, we can take 5 to the power 2 times 5 to the power 2, which is same as 5 to the power 4. We can take 5 to the power 4 times 5 to the power 4 which is 5 to the power 8, and so on and so forth. So the number of multiplications required here is proportional to the number of digits in this binary expansion. Again, we can compute each one of the necessary terms, and we can get the final answer by multiplying the necessary exponents of 5, and that will give us the final answer to be 3. What I want you to do here is I want you to verify this each step and see that you are able to actually do this. Now this is something you should be able to do without a calculator because the numbers we are dealing with are fairly small. Important thing to do is every time you compute these numbers, instead of computing these numbers in a whole, you will apply a mod 7 to each of them. That will keep your numbers small, and that will allow you to do this without a calculator. The next way is what we are going to do is we are going to study doing this with Fermat's little theorem. So we don't have Fermat's little theorem where the exponent can be arbitrary. We have it for a specific instance, which is 5 to the power 6 is going to be 1 mod 7. So this is what we can observe. 5 to the power 6 mod 7 is 1. Now from here we can observe that 5 to the power 1998 is going to be 1 mod 7 as well. Now where did we choose this number? This is because this is the largest number that is multiple of 6. 6 came from here. That is less than or equal to 2003. So we have 5 to the power 1998 is 1 mod 7. Now we go ahead. Now what is left is a 5 to the power 5, and we can compute that, take modulo 7, and that will give us the answer to be 3. I want you to verify what's going on here. Make sure that you can do such a problem if this number that you have in over here is a small prime number. Here is a way we can use Fermat's little theorem to do certain things. So for example, let's suppose we want to compute 5 to the power 2003 mod 13. Now by Fermat's little theorem, we know that 5 to the power 12 is 1 mod 13 because 13 is a prime, and we have 5 to the power 12, which is 13 minus 1, is going to be 1 in modulo 13 arithmetic. Now we can take this further. We can basically divide the number 2003 by 12, and what we'll find is that the quotient will be 166, the remainder will be 11. So we are going to write this as 5 to the power 2003 is 5 to the power 11 times 5 to the power 1992. So 5 to the power 1992 is 5 to the power 12 to the power 166, which is 1 to the power 166. 1 to the power anything will be 1, and therefore we can replace this whole thing by 1, and therefore the answer would be 5 to the power 11 mod 13. And therefore the answer in this case would be 8. I would like you to check which of these statements are true by Fermat's little theorem. The answer is there at the bottom of the slide.